All right, welcome to this mechanics masterclass. Today, we're tackling a real classic, a problem that's probably stumped you or your friends at some point, number 1.78 from Irodov's legendary problem book. Now, it looks like a complicated multi-body system, and it can be a little intimidating. But I promise, by the end of this, you won't just have an answer, you'll have a powerful method for solving pretty much any problem like it. So, let's dive in.
You ever just stare at a problem like this and not know where to even begin? Yeah, you are definitely not alone. It's a classic for a reason. But here's the thing. The key isn't some secret magic formula. It's all about having a solid step-by-step blueprint that turns the chaos into clarity. And that's exactly what we're going to walk through together, piece by piece.
So here's our game plan, our blueprint for the solution. We're going to move through these 6 logical steps, one after the other. Each step builds on the last, turning this big, scary problem into a bunch of smaller, totally manageable tasks. Let's get going with step 1.
First things first, before you even think about an equation or a vector, you've got to know exactly what the problem is asking. So many mistakes happen right at the very beginning just by misreading or misinterpreting something. So let's take a second and read it carefully.
Okay, let's read that carefully. Now, the most important phrase in this whole thing, right here, relative to the horizontal surface. That's gold. It tells us we are looking for the absolute acceleration of that small block m. Its motion as seen by someone just standing still on the ground. That is a really critical distinction, and it's going to guide our entire approach.
Okay, let's break this down. What do we actually know? We've got the masses, big M and little m, and the coefficient of friction, k, between them. What are we looking for? The acceleration vector of the little block m. And we've got a couple of key assumptions we need to keep in mind. The ground is frictionless, and the pulley and thread are perfect, massless and all that.
All right, now for what I think is the single most important step in any dynamics problem, the free body diagram. I'm not kidding. This is where you translate the real world into physics. If you mess this up, even a tiny bit, it doesn't matter how good your math is, the whole thing will be wrong. So let's be super careful here.
Okay, let's focus just on our little block m. First, the easy one, gravity, right? mg, straight down. Then, the wedge is pushing up on it, that's our normal force, n. And remember, it's always perpendicular to the surface. The thread is pulling it up the incline, that's tension, t. Now the tricky one, friction. Which way is the block trying to slide on the wedge? It wants to go down, right? So friction has to fight that. It's going to act up the incline. Okay, now for the big wedge M. It's got its own weight, mg, pulling it down. The ground is holding it up, so that's another normal force, we'll call it N ground. The thread is yanking it to the left, that's our tension, T. And now, here's the part that everybody forgets. For every push or pull that M felt from the wedge feels an equal and opposite one back from M. And this right here? This is the #1 trap in these kinds of problems. It's all about Newton's third law. For every action, there's an equal and opposite reaction. That normal force the wedge puts on the block, well, the block pushes back on the wedge with the exact same force. Same thing with friction. If you forget to draw these reaction forces on the wedge's diagram, and so many people do, your equations are doomed from the start. So please, always double-check for these action-reaction pairs.
Okay, our diagrams are looking good. Now we need to set up a frame of reference so we can turn these arrows into math. And this choice is actually pretty strategic. A good coordinate system makes the math way easier. A bad one? Well, it can turn into a total nightmare.
So we're going to plant our coordinate system right on the ground, an inertial frame. Why there? Simple. In a frame that's not accelerating, F equals ma just works. If we were silly enough to put our axes on the accelerating wedge, we'd have to deal with all these weird, fictitious forces. And trust me, that's a recipe for confusion. So let's keep it simple. X is horizontal, Y is vertical. Done.
All right, moment of truth. Time to turn our pretty pictures into cold, hard equations. We're just going to apply Newton's second law. You know it, sum of the forces equals mass times acceleration to each body and for each direction.
Let's start with block M. For the x direction, we look at all the horizontal forces. Now, some of our forces, like the normal and friction, are at an angle, right? No problem, we just use a little bit of trick, our sines and cosines of alpha, to find their horizontal and vertical parts. And don't forget our friction equation, that's an easy one. Friction is just the coefficient k times our normal force n.
Now, we do the exact same thing for the wedge M. In the x direction, we've got the horizontal parts of those reaction forces from M fighting against the tension. And that all equals m times its own horizontal acceleration. Now, in the y direction, things are simpler. The wedge isn't jumping up and down, right?
So its vertical acceleration is 0. That just means all the up forces have to perfectly balance all the down forces.
Okay, let's pause for a second and take stock. Count up our unknowns. We've got T, N, AMX, AMY, and AMX. That's 5 unknowns. But wait, how many equations do we have from F equals ma? Only 4. Uh-oh, we're stuck. We can't solve this. This means there's a piece of the puzzle we haven't used yet, a hidden connection between how these things move. This is what we call the kinematic constraint.
And here it is, the aha moment. What's the one thing physically connecting these two objects? It's the thread. Think about it. It's a single unstretchable thread. That means that for every inch the block M slides down the slope, the wedge has to get pulled exactly 1 inch to the left. The thread ties their motions together.
So if the distances they move are linked, then their speeds must be linked. And most importantly, their accelerations have to be linked too. And that is our missing piece. The size of the wedge's acceleration to the left has to be exactly the same as the size of the block's acceleration relative to the wedge. This is the 5th equation we've been hunting for.
Okay, quick physics reminder. How does relative motion work? The total acceleration of m that we see from the ground is just a vector sum. It's the wedge's motion plus the motion of m on the wedge.
And this is how that one constraint just cracks the whole problem wide open. Check this out. We can now write the absolute acceleration of the block, both its x and y components, not as 2 different unknowns anymore, but both in terms of one single unknown, this value a. We just went from 5 variables down to 3. That is a massive breakthrough.
And just like that, we're done. No, seriously, all the physics is officially over. We've broken down the problem, we've applied the laws, we've found that hidden link. Now all we have is a complete toolkit ready to put together and get our answer.
So look at this. This is our final system of equations. We just took our F equals ma equations and plugged in what we learned from the constraint. And what are we left with? 3 equations and 3 unknowns. Tension T, normal force N, and that key acceleration magnitude A. The physics work is done. This is now just an algebra problem.
So from this point on, it's really just a matter of rolling up your sleeves and doing the algebra. You've got 3 equations, 3 unknowns. You can totally solve this. A good strategy? Maybe use that second equation to solve for n in terms of a, and then plug that into the other 2. It's a little bit of grunt work, sure, but the path is totally clear. Once you solve for a, you've got the key. You've already solved the physics part.
So let's just step back and look at the blueprint we used, because this is what you should take away for any problem. First, we deconstructed it. Then we drew our free body diagrams like our lives depended on it. We picked a smart coordinate system, we wrote our F equals ma equations, and then, the secret sauce for this one, we hunted down that kinematic constraint. This 5-step process, it's your key to solving so many of these dynamics problems.
Look, this whole exercise wasn't just about getting the answer to Irodov 1.78. It was about building a method, a process you can trust. So the real question I have for you is, now that you have this blueprint, what's the next complex problem you're ready to go out and conquer? Thanks for joining this explainer, and good luck with your next challenge.